Okay. So this is the 2160 lecture 6, partial least squares regression. So we introduced the PCR principal component regression last time. But I know that there's some certain limitation to the PCR. So based on that, we introduced a little bit more advanced method, which is interestingly not being used in controlled and robotics community, but instead it has been used widely in chemistry and then biology and some social science area. But it turns out to be a very useful, powerful method. I don't know why. The different disciplinary areas, they do not communicate and they don't know what's going on the other side. So this is one interesting example. How interdisciplinary approach is very important. So we look at this from the statistical theory viewpoint, and it's obvious to extend the some of the simple method to this direction. That's a partial least squares regression. So the last time we look at the principal component regression. So we characterize the input data space, right? And they reduce the input dimension based on the principal component analysis. So that basically look at the eigenvalue problems associated with the input the data covariance matrix, right? Before that we do mean centralizations. Okay. And then also it turns out the high dimensional input space can be reproduced with just a fewer number of latent variables, low dimensional set of variables z1 to zm star. We call this latent space. And to predict the output y, we regress on these latent variables. What it means is that if you use just a linear relationship, and so each of the output y1, for instance, is a linear combination z1 to zm, and you need to identify the weights and parameters associated with it, and you have to do this for L times, right? That's fine. However, now you appreciate that because this input dimension is much low dimensional, the number of parameters involved between here and here is much smaller number than doing this. From here to here, you have to estimate so many parameters. It's very difficult to do, but condensing the input space to this extent, then the job is much simpler. Sounds reasonable and sounds great. However, there's a very well-known caveat in it. The caveat is, somewhat quietly in principal component regression, we assume that some component having the large eigenvalues may be very important, large significant component. Also has a large actually footprint in the output space. Including this mode is important to predict the output y, right? So as you go here, there's some kind of strong relationship between the two. So the question is that in this guy, having a very small, eigenvalue and the input, covariance, matrix, we quietly assume that such small, mode, small component in input space may be negligible, not too much significant in predicting output y. Well, that is somewhat questionable, right? Because we look at only input space. How do you know that this one is insignificant? In fact, there's some case that small components in the input space may play a very important role in predicting output y. On the other hand, there's some mode which is some decent importance, in the input space. Turns out the kind of relationship between this input, this mode, and then this output is almost random. You can't say much about, by knowing this, you can't say much about the output. They are weakly correlated. If this is the case, this is not actually a significant component, right? Instead, this one, you should not actually ignore that. You should take into account that this must be involved in the input space, even though you reduce the space, right? So here's the point that we need to think a little bit on the more carefully. How do we know which one's important for the purpose of predicting output? Why? What comes into mind? Surely we should not just look at the input space alone, right? Yeah, we have to look at both input and output, right? And then maybe correlation is one mathematical tool that we can use. So in fact, components having a significant correlations, between input and output must be involved in the latent space. And this requires to analyze both input and output spaces rather than characterizing the input space alone, right? And also, looking at the output, which is actually, a multivariate, okay, vectorial quantities. You may find that, say y1 and y2 are very much collinear, all right? Or, once you have a y1, the y2 is almost redundant. If they are strongly correlated, right? So, now we need new tools, right? Output space Y2 must be considered, right? This lecture today will focus on the latent space modeling based on input-output correlation analysis, input-output correlation analysis. Okay, now how we really do that? So, the method that we take is, somewhat similar to the method we've been using, input space. So we have so many data points involved in the data matrix. And we probe around this by considering a unit, the vector pointing all the directions. And we look at the, projection onto that unit vector, and then actually characterize, how much they are actually having components in this directions, right? Now, interestingly, we do the same for the output space. So output space too, we consider some directions, indicated with the unit vector, and then look at the projection onto that. We do this, and then once you actually set up this, we can actually formulate some correlation between the components along these directions and the components along these directions, right? So that is actually mathematically written in this way. This is the method called the partial least square regression. Need 3 steps of operations procedure. So this is the first step. Step 1, find the directions of a pair of unit vectors, V in input space and the W and the output space, that maximizes the correlation between the projections of input vector onto V, which is actually V transpose X, that's the inner product, right? Z, and that of the output vector. Okay. So input space, we consider this unit vector V, and projection onto this is basically going this guy Z equal V transpose X. Now this value Z is basically is called the score, input space score. Okay, and we do the same for the output space. Now consider unit vector W and then projection, y is now, it's not a scalar, but a vectorial quantity, right? So y, projected onto this line, and this is the, length from here to here, right? And this R is called, score of output, output y, score with this, in terms of the direction, the W, okay? So we actually evaluate the scores, basically, inner product or projections, in both the input and output, that's Z and R, and we look at the correlation between the two. So what is the formulation, the equation formulating the correlation? That's actually, you take the product, right, of these two random variables, and then actually take the expectation. This is the correlation, right? I quietly mixing the, random process versus a specific data space. Suppose we have many data points, and we can apply some of these statistical analysis, and then that's actually for the brevity of expressions. I use expectations rather than taking summations, and that's very lengthy expressions. And so let me use the E. And I think and what I mean by that is very is clear. Okay, so let's compute this. Z by definition is actually V transpose X, right? And R, by definition, W transpose the Y. And now here, X and Y, input output space data points are random variables. V and W are not, right? So this expectation applies to X and Y, right? But you have to make this one to be dimensionally consistent. And this one, you can replace this one by Y transpose W, right? And then X and Y put the back and back to back. That's actually resulting in this. And we can factor out the W and the V, which are not the random variables. So we can write it this way. Okay, expectation X times Y transpose. Now, X, expectation XY transpose, this one is a little bit more involved. So let me just, do this, just quick review. Covariance matrix. So both X and Y are, vector quantities, right? X is actually column vector like this, and Y transpose and a row vector like this. So taking all product between two vectors, you get the this expansions, right? So each of them, well, we can actually take the expectation for each of them. So and I write this, but inside of it is basically this one, and we write this covariance of XY, product of XY. Now, since we assume that prior to this, the data analysis, we have completed the mean centered and the normalization, so we can make an apple-to-apple comparison, and mean value has been subtracted. So covariance and the correlations are basically the same. So we use the covariance and the correlation in an exchangeable manner. Which I hope not actually confusing for you. Okay, now here's the problem, right? We like to maximize this quadratic form. Turns out this is a scalar quantity. V transpose and covariance XY as we discussed, as we derived there, and then actually sandwich to with the W. Okay. And we like to maximize this correlation. Subject to B and the W each is actually unit vector, right? Unit vector. So what comes into mind? We use the same type of mathematical tools. That's actually Lagrange multipliers, right? But see here, it is actually plural multipliers. Because we have two constraint conditions to satisfy. So one for this guy, V transpose, this can be expanded to the V transpose V, right? -1, this must be 0. And for this constraint, we put the Lagrange multiplier lambda v. And for w, we have yet another Lagrange multiplier lambda w. Okay. And then actually, we put in all together and create the new Lagrange function. And what we'd like to do is to, maximize this, right? Now, all constraint conditions have been incorporated into this. So we are ready to compute the, maximum value, okay? A function of both and v and the w. So it is actually two variables involved here. Okay, cool. So what you want to do is basically, maximize or minimize this. So the sufficient, necessary conditions is that the first take the partial derivatives with respect to v, set that one 0, and also partial derivatives with respect to vector w, and set that one to be 0, right? Right. So we do the same, the differentiation. First, let's differentiate it with respect to v, and then it comes out to cxsw, and from here, 2 comes out, and then actually cancelled with 1/2, and the lambda, v. And actually, the other side is we get a very similar expression, but differentiated with respect to w, comes out to this. Yeah, here's the important point is that this one, when you differentiate it with respect to w, you have to actually take the transpose, so it comes out in this way. If you are not so much sure with this type of differentiation of a scalar function, scalar quantity with respect to a vector, just go back to the component-wise differentiations, and each component you get some results, and then put them together. You get these vector matrix form. Okay, we use this relationship cross covariance CXY transpose equals C sub YX. This one is almost obvious, but let me check. Okay, so taking so by definition CXY is something like this, right? And then take transpose. All I need to do, I just swap these two to get to this expression. So now let's change the x and y here, which doesn't do any different things. So just take the product differently, and this can be written this way: y column vector times x row vector, and then what it does is basically cyx. So here's actually the same. Or the key part is just the inside of this, the two vectors in here, and take a transpose. When you take a transpose, and you have to change the order, y first, followed by x, take transpose again, then this comes back, and then this is it. Yeah. Okay, cool. So we got the these two equations. Okay, this one and this one. Now, very interesting thing is happening from here. So let's solve it further. So from 36, okay, we can, lambda v is nothing but just the scalar quantity, right?
Professor?
Yeah, go ahead.
In equation 36, there was a question about whether that should be lambda sub w.
Oh my goodness. Yeah, that's lambda w. Yeah, this one is, typo. Lambda w. I'm sorry about that. Yeah, lambda w. Did I make many change here? W. Yeah. So this one, the w. Right. The w. I will post the some revised version. Equation 36, right? 36. Yeah, I'll make some corrections and post it tonight. Yeah, sorry about that. 36 B should be W. Thank you. Okay, good. So, and then, yeah, so solving this one for, the W. So 1 over the lambda W, C, YX, V, right? And, let's substitute this one into 35, replacing this W, and then clear, lambda W. What you get is CXY, and here CYX and V equal this side lambda V and the W lambda W times this V. Okay, so if you look at this equations, okay, you know that these are scalar and these are matrices. What comes into your mind? Vector multiplied to matrix turns out to be vector in the same directions with this scale, right? So this is exactly the eigenvalue and the eigenvector relationship, right? So it turns out that this vector V, an input space unit vector, is the eigenvector of matrix CXY, C sub YX. Okay. Doing the same for this equations. So V equal 1 over lambda V times CXYW, right? Substituting this one into the second equation, you get the very similar, but slightly different ones. Here you have a CYX and CXY times W equal the same scalar quantities times V, W, excuse me. So W is again the eigenvector of this matrix, right? And the product of this one is actually eigenvalued. This implies that the vector W is an eigenvector of matrix this guy. Oh, so now we know what we are doing, and then actually V and the W can be determined by computing these matrix eigenvectors, right? But here the thing that this has more interesting properties. So we get the two equations, right? Now, note that in both cases, the eigenvalue is the same, right? Lambda V times lambda W. And it turns out the lambda V and the lambda W are the same, but we can prove it very quickly, So, let's see, pre-multiplying V transpose to 35. 35 is just this equation. So pre-multiply this guy here. So V transpose CXY W minus lambda V transpose V. This one is nothing but just a vector norm, right? A square. So that's 1, right? So the lambda V equal this guy. You get it. Now, similarly, 36, we multiply the W transpose, from left, right? And actually, what you get here is lambda V equal W transpose CXY transpose V, and as a whole, this guy is a scalar quantity. So if you just take the transpose of all these, it doesn't make any difference. So doing so, V now V transpose, the next one CXY, and then the W comes in. This guy is exactly the same one as this. So lambda V and lambda W are the same. So the Dutch said actually these two matrices, although different in dimensions, and have the same eigenvalues, okay? The same eigenvalues. So we can write it, and this one to be lambda square. Okay, and with this, we are ready to introduce the singular value decomposition. Singular value decompositions. And I guess many of you that have actually, seen this singular value decompositions in other subjects and other places, and right? I guess at least you have heard the name, or professor just said that use it, believe me, I know, it's that kind of stuff. It turns out the singular value decomposition, I guess this is one of the most useful mathematical tools that shown up very much repeatedly here and there. So, and then this, subject is not exception. We use this at least twice or three times. Okay, so let's look at that. Okay, this is the extensions of eigen decomposition. It doesn't have to be applied to a square matrix, but it works for rectangular matrix M by L, let's say. Okay, M by L, and then this one is to be decomposed to, it's basically factored to V, D, the W transpose. And here, V, capital V, consists of small v's, and they are called the left singular vectors of matrix A. In fact, these vectors are nothing but the eigenvectors of matrix A transpose, which is actually M by M, okay? M by M. And then this matrix, is actually symmetric matrix, right? And then the real. Therefore, this matrix has all real eigenvalues and eigenvectors. So these are meaningful, physically meaningful eigenvectors, okay? And the W components are called, right singular, vectors of matrix A. And then it turns out that these are eigenvectors of matrix A transpose A, which is actually L by L, okay? And again, this one is, symmetric in the real matrix, having all real eigenvectors. Now, being sandwiched, by these D and the W, it's a matrix D. This one is a type of a diagonal matrix, but depending on the dimension, the M and L, it takes a different shape. But in case M is larger than L, this is actually, vertically long in a square matrix, having the, upper part of diagonal elements consist of, S1 through SL, where SI being the singular value, not the eigenvalue, but the singular value of matrix A. That's a good name. And in fact, what's inside of it is that, the square root of non-zero eigenvalues of matrix A transpose. And this one and this one and have the identical eigenvalues, and they are non-negative. So if you take the square root of it, you get the singular value that's actually sitting, across this, okay? So that's actually singular value decomposition. And you can see our analysis and finding the strongest correlation between multidimensional input space and the multidimensional output space. We end up with the cross correlation matrix, right? That's basically a not the square matrix. Turns out it is a rectangular matrix. And then we can apply this, and then we can find the V and the W, and those are, the ones that we're looking for. So here's actually an application to our, partial least square regression. The unit vectors, optimal one, V optimum, and then W optimum, that maximize the correlation between input and output scores. Z equal this guy, the R equal this guy, okay? Are the left and the right singular vectors. These are basically singular vectors associated with the largest singular value of the cross correlation matrix, CXY. So CXY is N by L, and then that can be decomposed into this. And if you take the first component, if you actually place singular values in descending order like this, sigma, S1, S2, in this way, this is the most significant one, corresponding to the maximum correlation between input and output. And that happens when you look at the input in the V1 directions and output W1 directions, you get the maximum correlation between the two. Cool. So that's actually the story, how we can find the maximum correlations between input and output. Okay, now with that, in step 1, we have found the component of the input space that is most correlated with the output, right? So how do we really correlate that? And then the output Y is to be predicted from the input score. So now we predict the output Y based on the score Z equal V transpose X. So now, what we did was actually high dimensional input space, looking at all the directions, end up with one particular one. And then score is Z, and based on this single scalar score, we like to predict some part of some components of Y, right? So, now Y is to be the functions, Y is to regress on Z. So, it can be written in this way, Y the sum, parameter vectors Q to be determined times the score Z, right? Since we have to predict the vectorial quantity Y, so Q must be a vectorial quantity. So it's not just, one axis Y, we have many axes Y, and we need to find the slope for every component of Y. So what we like to do is we like to find such, Q that's actually most effective to predict the Y, right? So we look at the prediction error. So that's actually Y is actually observed in the data. And Y hat is the one that predicted in this way. And we like to evaluate the prediction errors and square the prediction error. And we minimize it by changing this Q to better fit this guy, right? So now it is conceivable the answer to this is that this Q is aligned with the W. That is actually the optimum unit vector, which is actually most correlated with the input, right? In fact, the W is basically aligned with the this vector Q. Although we need to adjust the scalar magnitude, so we need to actually identify Q. But what we like to do is to just minimize this, evaluate this one, to optimize this. And in that way, we like to find the Q. It turns out the Q is aligned with the W. That can be proven in a rather simple way. So I'd like to leave it to your problem assignment next week. So so what you would like to do, we like to find the Q that is to minimize this squared error, right? So the Y hat is Q times Z. The Z is actually a score, right? So that is actually given by input vector unit vector V transpose X, right? So putting this one in here, we can write in this way, right? So again, we can actually expand this. So this is just an expansion of this product, right? Just a simple expansion. Then we have to look at this, and which are random variables, which are just parameter or vectors. Well, here this is actually in here Y and X are actually random variables. So we need to relocate the scalar quantity. This is inner product, right? Scalar quantity. This can be shifted from here to here. You end up with this one, so that the X and Y are placed back to back. And for this, we can apply the expectations and factor out this to both sides, and you get to this expression. we can do the same for this, and it turns out that this is the solution. So yeah, what we like to do is to take the derivatives with respect to q, exactly the same type of mass. It turns out that this times v equals b. We have two of them. So q we have two of them. So we get the 2 times the q v transpose is something. Okay. Yeah, but please do it on your own. This kind of computation, you need to convince yourself. Okay. It turns out this part is actually CYX cross covariance, and this one is actually covariance of CXX, right? So solving this one for Q equal CYXV over V transpose CXXV. So I have to be scaled by this quantity. And this particular vector Q is called output loading vector. Output loading vector. Okay. So we just finished one variables. Let me just cut here. I want to take any question at this point. I hope. Let me see. Stop sharing any questions. Oh, chat. Oh, good list. Oh, 36 should have lambda W, not lambda. Oh, thank you. Yeah, that's actually my mistake. Yeah. Barin. Yeah, the W matrix is L by L. No, the W is actually a vector, and the dimension is L by 1. Oh, did you write the L by 1? Yeah, both are ones.
No, he's talking about for the singular value decomposition. The W matrix on the right side.
Yeah. Okay. The W big, capital W matrix. That's basically yes, L by L. So the singular value decompositions. CXY is small m by L, right? So B is m by m.
On the slide, I think there was a typo. The last column of the W matrix had a small w and with an M subscript. It should have been an L subscript.
Okay, sorry. Did I make any mistake? So, what's the equation number? Oh, okay. I'll check it. I'll check. Oh, well, by the way, I posted the slides, which is a little arty version. I made it, but I know until the last minute before I give this the lecture, I go through it many times and then make some corrections and changes. I just change the order and add more explanations. It's basically endless effort. So but maybe that's actually a kind of a typo is something that I have to check. Yeah, I'll do that. Sorry about that. Yeah. Yeah. Right. So does Q have the same direction as W, but the different magnitude? Yeah, Charles, you are right. That is exactly the case. Different magnitude, but it's the same direction. Yeah. Okay. With that, let's go back to the second half. The second half is a little tricky. Okay. So up to this point, it's fine. However, we found only one set of latent variables, right? We really need to find more, right? An accurate prediction that cannot be made with just one set of latent variables. Oh, by the way, we use this, terminology, latent variables. Latent model is something not actually directly visible in the original data, but behind that the data, we see some structure, we see some more succinct, low-dimensional expressions, right? That we call the latent models. And then actually latent models is described with the multiple variables. Well, in our case, we have already introduced quite a few variables. One is input vector v, and output unit vector w, and the score, all right, z and then r, right? And then also we introduced the variables q, which is actually which is called the loading vectors. So these sets and these actually variables form a set of latent variables. So that's one set, okay? But we need more, right? Second, the most significant, third, the most significant, latent variables. Unfortunately, if you just go to a singular value decomposition, well, you see that, hey, number 2 is already there. V2 and S2, W2, it's already there. But unfortunately, it turns out that's actually this pair, this set of variables are not actually the most effective, second most effective, most correlated set of latent variables. We can actually find somewhat similar, but slightly different directions, we get the better results. So we need to do it, okay? Yeah, to actually find the second optimal set, we need to go through the process. It's called deflation, okay? Yeah, when we hear deflations in New England, it's really kind of bad memory. But yeah, so a little bit of cheating, I believe that's not his fault, but I know people hate him. So yeah, that's actually we've been too strong for many years. Anyhow, deflation is the kind of process that we had to go through. Okay, predicting output y based on the first set of latent variables, we have used some components involved in the data matrix already, right? So those things which we have already used must be put aside, or must be eliminated from the data matrix. So after we clean up those things which have been already used, then we can apply the same technique to find the second most correlated directions, okay? So, this component of data matrix must not be used for determining the second most significant component. So we have to remove the components already used in the first round of predictions, okay? And examine the residual components that have the highest correlation with the output. So, output the data, this one is easy to think about. Original data is actually y1 to yn. That's actually a sample point. And we like to, subtract the components used for the first round output predictions, right? And then we eliminate that, and then we use this residual part. Well, using the output loading vector Q, right? This is one that we use for prediction. So, multiplied with the score Z is actually the, input unit, input space, every, vector X inner product with the unit vector, V, and taking the inner product, you get the score Z, right? So, that times the Q is actually part of the, output Y that we predicted based on just the first, set of latent variables and Z. So, we have used that. So we have actually successfully predicted part of Y, in this direction. So we subtract this one from y, leaving just the residual here, y prime. So we treat this one as a fresh, new data, and then we apply the same technique, as step 1, step 2. Now, the input data matrix side is a little bit more involved. Yeah. So, collectively, X consists of, X1, X2, and, the samples and we taken for, N data points are all involved here, right? So we're to do things in this way. So let's look at that. So what we'd like to do is actually input the data deflation and finding the components used in the first round, okay? So, and not just looking at the one particular, data point, but we have capital N data points in the samples. So, let's look at this data matrix. Okay, data matrix again, the concatenations of all, the data we have collected from 1 to capital N. Here, upper script with parentheses 1 to N represent the the data point number. Okay, first to capital N. We have many of them. And each vector is actually m-dimensional vector, so it has m components like this, right? So now, yeah, for each of them, for each vector x1 to xn, we have computed the scores, right? Scores. Z is score. In the direction that's actually optimal direction v has been set, and then look at the projection onto that unit vector. You get the z for for this sample and first data points, and the second, and then capital N. We have capital N components in here. Let's define this to be a capital N dimensional vector z, okay, z. And this one is one that we have already used for the first round in prediction. And let's look at the this data matrix. We view this row-wise. So putting this one into just a one vector, C1, that's actually 1 by capital N dimensional row vector, okay? And we have totally m row vectors, taken from this data matrix. Okay, now let's plot this, z in capital N dimensional space. So, we have some axis associated with the data, number 1, and the data number 2, and the data number n, right? And first we plot the z, consisting of these components. It takes some particular coordinates in the m-dimensional space, right? And actually, this is the directions. Again, we have used the information from the original data input the data matrix in the first round. So now let's look at the this data matrix and view it row-wise and plot the C1 to Cm in this n-dimensional space. So each actually row vector is to take some point like this, right? Some point like this, and points. Now what we'd like to do is to subtract the information taken in the first round operations. So this is the directions in which we use the information. So for each of these actually an original data points, we make a projection onto the plane which is perpendicular to this capital Z. In other words, we projected this in parallel to this vector Z to this point. And let's see, C1 is mapped to C1, Ci prime. So, we eliminate the, these components, and look at the, hyperplane within this that is a one-dimensional lower, from the original one. And we like to construct these set of data points. Now, what we can do is to project this one onto this. So first, look at the this vector ci, excuse me. So what we like to do is to find this component, right? So OB, vector OB, is obviously vector OA minus vector OC, right? Now OC, we know the the direction is determined by Z, but let's take the unit vector, well, this guy, so divided by the its own magnitude. So this becomes a unit vector, and then we like to project this vector onto this by taking the inner product. So Ci and then this unit vector. Now, the little tricky part is that both Ci and Z are row vectors. So usually we deal with the column vectors. In the column vectors, Ci transpose Z, right? But because the row vector transpose is placed here, this one is already row vector, and then this with the transpose, this becomes a column vector. So this is actually inner product. Okay, but anyway, this term is to give this length, this length. Okay, so now we need to subtract from this OA Ci, this vector. This one is pointing in this directions, right? Pointing in this direction with this scale. Therefore, let's look at this. Ci prime, which mapped to this one, is original Ci minus. This is actually the magnitude of OC. And then this is the directions of this vector OC, in terms of the unit vector. So if we multiply these two, scalar times vector, subtract that one from Ci, that's actually Ci, prime. And here we can factor out Ci. So Ci prime is given by putting this kind of a matrix, which is a type of a projection matrix multiplied to this. So this guy is, we look at the, only one and a row vector, right? Only one row vector. We do this repeatedly from I equal 1 to I equal m. We get actually many of these, and must be concatenated, vertically. So that can be actually done by replacing this one, capital X prime, and this one capital X, just as defined here. We put in this one in this way, multiply the same projection matrix, this. So this is our final result. Basically, input the data matrix is basically reduced to this one with this projection. Now, well, we can do the following more useful analysis. So we like to rewrite this projections. Okay, it's a little involved. So note that the Z is originally basically concatenation of score, right? Score Z1 to Zn, totally n, some the data points, and each is computed by in this way, V transpose x1 to xn, right? So factoring out the V transpose, we can write this way. So these are basically a data matrix, V transpose capital X. So let's compute this guy, Z, square. This can be written as Z transpose. Again, please remember that the Z is basically row vector. So this representing an inner product, right? And then we substitute the above equation. Yeah, so Z is replaced by V transpose X, and with this transpose we just change the order. D being XX transpose, as we discussed before, if we have enough data points, this represents the covariance CXX times V. Okay, are you okay? Replacing this by this. Yeah, if you just write down, you can find the for large N, you can see this kind of stuff. Okay, so now this expression above one. Yeah, here it can be written this way, right? So distributing the capital X, and then distributing the X in here. And then this part, the denominator is a scalar quantity. Now we found that is actually given by this, so I put it in here. So I know, again, the Z transpose, because Z is this guy, replacing it, and we have XX transpose back to back. And from Z2, I know the V transpose X and a VB transpose comes back to back. So, factoring out the X from the right, because X is existing here, we can write this one in this way, right? So I know I replace this one by CXX. And X is existing on the right side, so we can factor out X from the right. So these two show the different format, although they are basically the same. So for each column vector, so this is the one that we got. This is the one that we got. Okay, data matrix is all collective expression. So if you look at the this, column wise, you can pick the, say, for instance, first one, it basically first vector shows up in this way, and the second vector, the third vector. In general, I just write the, any component here, X prime equal, I minus this matrix times X. And one last step is that I like to combine X V transpose times X. What that means? That one is again score Z, right? So this is what I did, putting out this and then replace this one by Z. And the rest of the part is basically this matrix, excuse me, a vector. And the denominator is basically a scalar quantity, and then this is a matrix times vector, so it's basically vector, right? And then we replace it by P. P is this guy. This is called the input loading vector. So deflated X prime is given by subtracting score Z in the directions of loading vector P, from the original X, that's actually to give you the deflected, X prime. So now, this part is a little bit, we need to think a little bit deeper. So to help you understand what we are really doing, let's look at some properties of deflated data matrix and input the loading vector. So interestingly, we can show by using that the input the loading vector P, okay, the deflated data matrix becomes very much most compact, compressed. So in capital big high dimensional space, we have many sample points here and there, right? And then we first find the first set of latent variables, and we basically use some component from that. So residue, if the first round is very effective, and then we take the most of the information from the original data, the residue of the data matrix should be very much small, compact, right, small in size. So let's actually test out this, whether that is the case or not, the smallest. So we look at this measure, right? So, x prime, this is actually after deflection and deflations, and we got the x prime. And we evaluate the mean squared norm of this x prime. Okay, and at this time, we like to actually confirm whether this loading vector P is the one that is to make this one minimum. So x prime is actually given by this, and originally it comes from this, so it can be written in this way, right? I minus b transpose x. So replacing x prime by this, putting this one back to back, and then expand it, and then take the derivatives with respect to p, the same story as before. You end up with this expression, and then solving this for p, what you get this. This is exactly the same answer, same vector as we found in here, So, this way of, deflating the original, data matrix really makes sense. Because after taking it, the residual in the data matrix is actually minimum in size, and the average, magnitude of x prime is actually the minimum. We found the p to be a minimum, and is the most effective to reduce that, and that the p is the one that we obtained in the previous derivations. Okay, so this is actually a deflation. Input to space. So we use this, kind of a mass to project this one to this, and output side of a deflation. It's very simple. You just remove this one, which has been used here. So some of you may feel that, why P is not aligned to V. V was very found, to be most effective directions, right? Well, interestingly, just deflating in the direction V, it doesn't give the optimal one. And if CXX, involved here and here, if CXX is identity matrix, if this one identity matrix, okay, is identity matrix, this one collapse, right? And identity matrix, this becomes basically the original V vector. So they are this guy and P, and then V are basically the same. But in case CXX is not actually spherical, the round one, instead it has some directional anisometric properties. There's some chance to get the even better results for the second round by taking this loading vector P instead. Okay, so we are getting close to the end. So we now know how to deflate the input space and output space. Now, what we need to do in the second round is that for the deflated x and y, we need to compute their covariance matrices, right? So definitions expectation x prime transpose and as such, right? so let's compute this one. Just a simple computation. Putting the deflation formula, x prime is actually deflated from x based on this expression. P is loading vectors, right? So putting this one here, the back to back, and here the random variables, and the expectation comes out that this is now replaced by CXX. And expanding this one, we get the 4 terms. However, look at the last term. This one, if you see from here to here, you can use this definitions of the loading vector. P is CXXV over this quadratic form, right? So, if you multiply this one to both sides, this is equivalent to this. P times that quadratic scalar quantity equals, this part, right? So, looking at this, P, V transpose CXX V is basically same as this, thereby replaced by this. If you replace by this guy by this, it's basically the same expression as this. These two cancel out. The result is this: CXX minus P, V transpose CXX, and factoring out the CXX, we get this expression, which is interesting because it's very similar to X vector deflation. Covariance matrix too can be deflated in this way. Okay, and similarly, this must be computed in the same way. We can prove that this is the case. Okay, so that's all about it. Yeah, just in summary, we repeat this process m star times until you get everything that you can extract from the original data, right? So step one, we set the original data, X and Y, to be the covariance matrices involved in here, right? So this is round one, okay? And for this, you compute the singular value decompositions and find all the set of latent variables for the first round. And after completing that, going to second round, k equal 1, so this is second round, the CXX2 equal to this times CXX1. So recursively, you compute this because that is the equation we have obtained, right now. So we can update both, CXX and CYX, for the next round, like this. So this is further deflated one, okay? Here, loading vector PA, P in stage K, and then Q output loading vector Q in stage K can be computed in this way, right? Doing this K times, M star times, you can predict the output Y, by this much. And here's the remaining part. This is residue, and after M star, cycles, you still have some error that is actually left in there. So compared to principal component regression, this partial least square regression is a bit more involved. But we look at the both input space and output space and find the most correlated directions. Let's look at the example, or shall I take the some question? May I check some questions after that? Yeah, not too much. Okay. Maybe you lost a little bit. So this is actually, yeah, no involved. But let me show you some examples to get to some real feeling. And I take some discussions and after that. So this is very simple, academic exercise, the toy program. Input space is 3-dimensional, and output space is 2-dimensional. Okay, 3, and 2. And we create some data. So this is 100, sample size, and x1, 2, 3, and then corresponding y1, y2 are created based on. So this is actually a true relationship, y equal bx. But to make the problem a little bit realistic, we put this noise term g. Noise g is basically a Gaussian noise with the 0 mean and 0.05 variance, right? So we create a very much random data, and actually B shown here is the correct one. Okay, so with this noise, we created this 100 the data 1 to 100. Okay, so this is the starting point. Now you can compute the input space xy x1 to 3 input space covariance like this. So this is fairly actually spherical, having all one components in the diagonal directions, but all diagonal elements not zero. Therefore, it has actually correlation in the input space. X1, X2 to some extent correlated. X1, X3 also correlated, right? And then actually cross correlations between X and Y can be computed in this way. Okay, or you can provide C X sub X Y. That's actually transpose of this guy, right? Transpose of that. Okay, with that, first around the latent variables, we do a singular value decomposition of the cross correlation matrix CXY, and then we pick the first most significant singular value and associated singular vector, left singular vector, and the right singular vector, and then that's shown up here, B1, and then W1 shown up here. Okay, so plotted here, B1 pointing in this directions, and then the W1 pointing in this direction. Now for this, we can compute the loading vectors, input loading vectors, and then output loading vector shown by these equations. We compute that. The result is shown here, the P1 and then Q1. P1 is, in this case, slightly different from V1. So almost the same direction because the original CXX is almost round, right? So they are similar, but it's actually slightly different directions. And then output side is basically pointing exactly in the same direction, but the scale is at the magnitude is different. Okay, now going to the second round. Here's the actually more informative pictorial representation. So first round, we see 100 data points are actually shown here, right? And then singular value decompositions reveals that the most correlated direction in the input space is this direction, and output space in this direction, B1 and the W1. Okay, they are most correlated. Okay, once we have set up the Q1 and then predict the part of output Y, then what? Then we go to deflation, right? Deflate the input data and the output data. Output data is simple because in this direction, the W1, we actually reduce this one in this direction. So you can put them together into this, right? Now first round input space, it is to be squashed, projected into that actually particular directions, capital Z, remember. And that it turns out that the P1 is actually the direction, so that is actually most compacting directions. So here in the P1 direction, we just reduce that, and then this one is projected one, which is basically lost the kind of this longitudinal directions and actually squashed into this, compressed to this data points. So now what we do is actually treating this as a fresh set of input and output data, and we apply the same technique, singular value decomposition, and we found the V2 and W2 is a little harder to see, W2 to be most correlated. And then we found actually loading vectors and then predict that. And the third step, it's almost nothing in the input space, a very small residue. And the output space is basically no change, which means that up to step 2, we have taken almost everything. And the remaining part is actually just a noise. Remember, we put the this Gaussian noise in here, very small Gaussian noise. That's at the end of the day, it remains here. So from here, you can't get any meaningful information, no structures involved. So it just actually garbage, is left here. But you have taken all the significant information up to this point. So that is the story. Yeah, we have many applications area, partial least square regression. As I said, the chemistry and biology are 2 major areas, and the biomechanics. I guess people are now using the IMU, placing that IMU at the many part of the body, right? I think Harvard group, I heard that they are using the an IMU. You guys are putting that in the legs and then torso or some upper extremities, and I don't know where you are putting, but I know that kind of data is a high dimensional. And if you take the time series, the data of that, it's an even a higher dimension. But you can actually reduce that, very effectively. Let's see. Let me show you some a little bit more entertaining stuff from now, and just talking about the application. So I think part of the I show this. Yeah, and then so first the
robot will try to act according to what I'm doing.
Robotic arms come to life thanks to artificial intelligence.
So he's wearing the IMU over here.
The system monitors the wearer's arm movements,
yeah,
and eye trackers
right.
detect where the person is looking.
So that's actually things in here, right? Yeah. So he's just lifting this, and the robot comes in, and the robot can predict where the arm to be placed, right? So that's good enough. So the technique that's being used is this. Actually, in teaching this kind of desired motions, we had the second person, red shirt guy, is holding the arm and then move this around, and as the lead the humans is moving around. Okay. And then actually extracting data, and then transfer that actually a relationship to this robot and to automate this process. So in here, all measurement coming from IMUs of the lead persons, and then not just a one time slice that we took many time slices, setting some time windows. So it turns out the input space is a 360 dimensional input space. And we had the 100 data points. So that's actually, the data matrix for input and output side. And the robot has, 2 arms, and each has 4 degrees of freedom. So 8 DOF in total. So this is actually output space, 8 dimensional. Okay. So, we applied the, principle. Partial least squares, regulations. The first component, the second component, the third component explain the situations, data up to this point. We truncated with the 3 components. These are coming from the time sequence data with the time windows, right? But so this is the first mode. It has some time delay, but it's not just static motion, but we can take the time series data. So robot is to detect the human motions and then actually predict the desired the location, the desired movement that the human did. So we have the 3 modes, and then with that, when you execute that, as you move, then actually, robot comes in automatically and then does the job. Yeah, that's the story. Okay, so I just want to entertain any questions. If you have, should I go to stop sharing? Okay. So is there a general rule of some to tell when you reach the garbage phase? Yeah, that's a great question, Charles. Yeah, so there's actually quantitative metric when to stop, right? So this is recursive, repetitive process. So when to stop, when you see the garbage information, because we don't know the noise property initially, right? Nonetheless, we must know when to stop. And I think I wrote just a few pages, extensions on this theory in the lecture notes, which has been posted on the web. So please look at that. There's some techniques in finding when to stop. Yeah. Okay. And does PLSR perform always better than PCR? And is there any limitation to PLSR? Yeah, of course. So the big question that we started with today is that only looking at the input space, we miss something, right? Yeah, some component which is very dominant, very significant in the input space is not necessarily well connected to output, right? So the PLSR can capture this, and PCR can't. So that's one big plus. Well, limitation to PLSR, obviously this is still linear operation. So something significantly nonlinear relationship, it cannot actually capture that well. However, interestingly, nonlinearity, we usually think that nonlinearity is a hard animal that's totally different from linear stuff. But recently, well, not necessarily recent, people found that as you augment more variables, expand the input space, expand the to a high dimensional space, we can somehow approximate the nonlinearities very well. So that, of course, depends on the nonlinearity, some very sharp, discrete, jump discontinuity of input-output relationship can't be captured. However, some actually, say hard spring, soft spring, something kind of continuous, and then benign nonlinearities can be captured by having a more actually redundant variables. So if you intentionally express it with more variables, you can actually deal with some type of nonlinearity pretty well. PLSR and PCR too, based on that kind of notion. So initially we actually model this in a high dimensional space. Yeah, and then actually cut it out. Yeah, if that is not significant. The real data comes from the real complex nonlinearity, but we don't care as far as we can predict things well. That's all set. Yeah, we revisited this actually high dimensional issues a month later when we discussed the kernel functions, and then finally it's going to dynamics. So that's actually a Kaufman theory. That's actually we deal with the high dimensions. So we started with this, but going to some Kalman filter from next week. But we come back to this issue. So yeah, dealing with the high dimension, the large data, it's fun. It's absolutely interesting, and we can do a lot, even though it is actually linear. Yeah. So that's the conclusion today. Have a good one. Yeah. Take care. Bye.
Bye. Thank you.
Bye.
Thank you.